Yes, good morning everyone.
Morning, sir.
Okay, I just came to know that around 30-35 people turned up in the lab today. What about the rest? May I know the reason? What about the rest?
It's a rainy day.
Raining. That means if it's not raining, you will come. Okay. Right. Let us start with the practical, then we'll go to theory again.
Point टाकायला लागते
My copyright.
point टाकायला
Okay, so this was the first program we tried to do in embedded C. As you can see, it looks like C, but architecture is differing, so the behavior also will slightly differ from general C to embedded C. So when I declare using this data type, qualifier and data type, this is a qualifier, this is the data type, and both of them are keywords. When I declare using the qualifier along with the data type, it means this particular string is going to be allotted in the row. Okay, it is going to be allotted in the row. Whereas in C language, it will be allotted in RAM. But in RAM, which part of RAM? Which part of RAM it will go to? Is it code section, data section, heap section, stack section? It will be going into data section. Okay. So in general C, this entire information will be going into RAM, and the RAM is divided into portions called as code section, data section, heap section, stack section for your program. So this information will actually be going into the data section. Here it is not going to the data section, it is going into row, read-only memory. And here this is the RAM. When I declare it without const, it will be going into RAM. So this is modifiable, this is basically not modifiable. So what we are trying to do is we are trying to copy from the non-modifiable memory of the CPU or system into a modifiable memory of the CPU or system. That's simply what this first application or demonstration is. Now let us try to extend this application a little bit more. So I'll make a copy of this. Okay, so copy ROM to RAM. Okay, copy ROM to RAM version 2.c. Let's save it. Now let the first version be there. Add the second version. In the first version, I will remove it from not to be compiled. Okay, so it is not going to be compilable because I've given the option not to compile. Then here is the other one. Now I'm going to add some statements in the same code. So name of this source file, I'll just put it here. Copy ROM to RAM version 2.c. Now here I'm going to add something. So underscore attribute underscore first bracket. In the first bracket I'll put some location 0x100 implying 0 0 0 0 0. So this is the meaning of that. Then take another bracket put here 80, then take another bracket and close it. So this is the syntax. Okay? In the same way, let's copy this syntax. And paste it here, change the address to let us say 4. Now, compiling this changed source file, save, hit this button for compile or build, it's called. So you have the 0 errors, 0 warnings. Now come to debug. Now first we come to the first memory and go to the location 100. So you can see at the location 100. Okay, now come to this, go to the location 100. Okay, so now data has not been copied yet. So now I execute step by step. The difference between yesterday's program and this program is, you can tell now because you have observed it live in the class and hands-on. What is the difference between yesterday's program and today's program? Please tell me. Huh? I have mentioned the address. I have told the compiler that I would like this string to be allocated at this location of my choice, not location that you want to give. Okay, same thing for the RAM memory. I want the RAM memory at this location for this variable, not at the location which you choose. So this is called as absolute addressing. Did you experience this in C language? Were you able to place a string at a desired location of your memory? A memory location at desired location of your memory? So this is not possible in general C or native C language. Why? Because native C language works under the control of an operating system, and the operating system will decide what is the memory locations available and what can be allotted for your variables. But here we have a little bit of flexibility. There is no operating system. There is only compiler here. We're trying to translate the code into machine understandable code. So this compiler will give us a privilege, is giving us a privilege to select our location for the variables. Okay, this is called as embedded C programming. So embedded C is different from native C. Native C, embedded C. Native C is OS specific, OS under OS control. The embedded C is not under OS control. Okay, so embedded C versus native C. Take note. Let me just give me a second. I'll just put it on the notepad because it is not satisfying the screen space. I think this should be fine. All done? So take a note that the above syntax, okay, this is called a compiler specific directive. Okay, underscore attribute underscore and this syntax. This is called as a compiler specific directive. The above syntax, which is the syntax, is a compiler specific directive. It is a compiler specific directive. The above syntax is a compiler specific directive. Do not confuse it with preprocessor directive. Okay? It is not preprocessor directive. Preprocessor directive starts with hash. Okay? It is not a preprocessor directive. It is a compiler specific directive which aims to allocate variables at absolute or desired locations. Which aims to allocate variables. Which aims to allocate. Which aims to allocate variables at desired or absolute locations. Which aims to allocate variables at absolute or desired locations. All okay? So in this code, this part of the code is, you can say, compiler independent. Okay? Whichever compiler you run this logic, it is going to work. But this particular set of statements here may not work in all compilers. May not work in all compilers. It will be restricted. So this is that's what I said, compiler specific directive. Okay with this? Next, coming back to yesterday's doubt, somebody was asking about while one. I am sure that you have written so many programs in C language today where you never try to terminate your main with while one. Yes or no? Yes. Did you at least write any program in C where you encapsulate your logic inside while one? Yes? Then how do you expect to come out of while one? Okay, great. Any other? First of all, why you are putting inside a while one inside your main program? You want to go for infinite loop. So what condition you are giving to come out of the infinite loop? Through break you are coming out. But for what? On what terms and conditions you want to come out of that infinite operations? So based on certain conditions you are expecting to run the loop infinitely until you desire. When you don't desire further to continue running the application or running the program, you are giving a condition that if user gives this kind of input, then it should exit from that. Right? Okay. After the program exits out of while one, where does it go? After the program comes out of while one, where does it go? After it comes out of the while one, it comes to the end of main. After it comes of end of main, then it returns back to the startup code. It goes back. Where will it go? It will go back to the prompt, right? It is going to go back to the command prompt. It is through command prompt you are giving ./a.out, then it enters your program and starts executing the statements of your program, and you keep on executing the statements until you desire, then you give a condition, then it exits that while loop and then comes out of main and then goes back to the command prompt. That means the operations of your program have completed. The requirement of your program is completed. So your program is terminated and the control is given back to the command prompt where you can execute the same program the second time, or you can execute other programs. So whatever resources that were allocated for your program, who is allocating the resources for your program? Who is allocating? Please talk to me. Operating system. Because your program is executing under the guidance of an operating system, right? So OS is a manager for the resources required for your program. So OS has given some resources to your program. Program has executed, it has done its job. Then again, resources are taken back by the operating system. So when your program exits, control goes back to prompt. It means that the resources which were allotted by the OS to your program have been taken back by the operating system, which can be re-given to the same program or it can be given to some other program. But embedded C programs that we have written right now, this program is the only program that is going to run inside the machine. There is no other program that is going to run inside the machine but your program. So if your program ends, what should happen? If your program ends, logically speaking, with end of main, what should happen to the CPU? It will be in idle condition. Idle means that's what, there is no program. So no program means what is there in the memory. Let us say that this is your memory. Okay, let us say that this is the memory for your system and you have taken this portion. You have taken, say, this portion of memory in your system for your program currently. Okay, you have taken this portion of memory. Now this program is completed. After it completes, what happens to the CPU? CPU started to execute the program. From this instruction, moved on to this instruction, moved on to this instruction, like that. It came to the end of main. And then once it comes out at random, what should it do? What should the CPU do? It should wait for, how does CPU know that it should wait for user? Every instruction you are giving to the CPU is given by user only. So did I give any statement here telling the CPU that CPU should wait for user? Did I give any scanner statement? Then what should happen? I did not give any statement. So what do you think CPU will do? Just give me a guess. What do you think CPU will do? It has done its work. There is no while one. It has done its work. What do you think it will do? Can you define what it will do? Can you define what it will do? Can you explain what it will do? You cannot explain what it will do. That is why I am giving while one. That is the simple reason I am giving while one. I cannot explain what the CPU will do after my program. So I don't want you to do anything which I did not define. I defined this. This job is completed. After this, what it is going to do, I don't know. Because I did not define that. So it can do anything which I didn't define or I didn't expect. So I don't want that. I don't want that unexpected behavior. Hence, I am putting this, currently in this example, I am putting this while one so that the CPU will not exit this program at all, because after this program, there is no operating system where the control will go back to. In C programming, in native C programming, the control goes back to the OS. Then OS is giving you a terminal, a prompt saying that you execute this program again, or you execute some other program, or you create a new program. But after this program, control, where it will go somewhere which is not defined by us. Because the nature of the CPU is it has to keep on doing something. Why doing something? Because inside a CPU you have a register called as program counter. So program counter, design of program counter inside a CPU, in any CPU is like that. It points to an address location. It fetches, it increments. Points to the next address location, fetches, increments. Fetches, increments. Fetches, increments. So this keeps on going. And it will keep on going till the end of the size of the program counter. What is the size of the program counter? It is a 32-bit register. The size of the program counter is a 32-bit register. So what can be the last address the program counter will be pointing to? Can you compute? Please compute. Participate in the class. You will enjoy the class if you participate. If you just listen, it's no use. If it returns back to starter code, then what? Program is completed, no? Job of program is completed. Okay. What you are saying is, it returns to starter code, then what? Then what? If that is what you are saying, it returns to starter code, then what? Is it defined? Not defined. But in native C it is defined. If your program exits, is it going to starter code? It goes to operating system. You are saying it will go to starter code. Let us say it goes to starter code. After that what? Did you define? No, but there it is defined. When it comes out to the program, it goes back to OS. Yes. What is the yes?
So can you run that code without the while loop?
Save and cross compile. Come to debug. What is happening? You wanted me to run, I'm running. So what is your explanation now on this behavior?
Not terminating.
Huh?
Not terminating.
Huh?
It's not terminating the process.
It's not terminating the process, right? It is continuously executing. Did you expect this behavior? No. You wanted something which you expected. So something else is happening than your expectation. In C, once it comes to the end, it terminates. No more behavior of that program application. But here it is behaving in a different way, which is not defined by us. Our definition is present in the main. After main, what is happening, you need to know. You need to know that you have to go into the object code. You have to go into the disassembly, object code, and then see what happens after main, where the control is going. All that you have to find out. Clear?
I didn't understand why you put only while on of one, like why that condition specifically?
Why I have given while one?
Yeah, while.
I am just giving while one so that I am letting I don't want my program to go anywhere else after it has done its job. I don't want it to do anything which I have not defined after it has done its job. Because after it has done its job, what happens after it has done its job is not defined by me, and there is no operating system to take the control back and exit our program. So what it is going to do is not defined by me. So that's why I have given while one here, just to say that once the logic is completed, it should stop here and do nothing. And the only way to stop this program, now the important point here, the only way to stop this program is to shut down the system. But how do you stop your C program? It stops by itself and it exits, and the control comes back to the prompt OS. But this program will never stop, as you can clearly see. It is never stopping, it is keep on running. So if you want to stop it, then either you logically stop it or you physically stop it. Logically stopping is putting the while one. Physically stopping means you shut down, you power off. This is the difference of behavior between C, embedded C execution and general C or native C execution. Why? Because embedded C executions are running in a hardware where there is no OS. C programs are running in a hardware where there is already an OS. So, in your hardware, okay, this is your hardware. On top of your hardware lies your operating system. On top of your operating system is your A dot out. So, OS is giving permission for A dot out to execute, and after returning, control is going back to OS. But in our current hardware architecture that we are talking about, this is not present. So, my hardware is directly executing the executable file, which is not called A dot out here, it is called as .hex file. So it is directly executing A dot out. So after it completes executing A dot out, what next? Is the question. So to close that what next, I am giving a while run so that my program logically stops after what it has been defined to do, and it should not do anything after that. I don't want it to again execute, I don't want it to execute infinitely. I want it to only execute once right now. If I want this program to execute 10 times, I'll put a for loop for 10 iterations. After 10 iterations, again I'll put a while run. That it has done its operations for 10 iterations, after that it will do nothing. Clear with it? Yes. Now, this act of putting while one in embedded C programming, the act of putting while one in embedded C, it can be like this. You can have your main and put your statements and then put a while one like this. This is one way of writing embedded C programs. When we write embedded C programs in this way, we expect this set of statements only to execute once. This is only usually for testing purpose. This behavior of an application is only to test an application, test some logic, whether it is working correctly or not. But majority will be like this. Majority of the embedded C programs will be like this. So I'll go for some initial statements and then I'll go for a while one loop and then I'll put here statements and I'll close. Majority of your embedded C programs will be like this, or applications will be like this. We do some initialization statements. After that, we enter the main purpose of the application, and the application will be executing forever. It will never end until we shut down the system, right? It will never end until we shut down the system. So we call this kind of architecture as super loop. Super loop architecture. So one of the FAQs in interview, frequently asked questions in an interviews, what is meant by super loop architecture in embedded C, or why embedded C programs use super loop architecture in programming. Note down the question please. In embedded C, what is meant by super loop architecture? In embedded C, what is meant by super loop architecture? That is a question. Or it may be asked, why super loop architecture is used in embedded C programming? So the answer to the question, both questions are same. What is the answer? What is the answer? I gave you all the explanation. Because embedded C programs are going to run on hardware where there is no preloaded operating system. Okay? Embedded C programs are going to run on a hardware where there is no preloaded operating system. So your embedded C program is the one which is starting the control in the hardware, and it is the one that is going to end the control in the hardware. Right? It is the one which is starting the control in your hardware, and the statements that end in your program are the ones that is going to end the control in the hardware. Hence, we have to define the program as a super loop architecture. While it will keep on executing and doing that work forever. Single tasking application. What is the purpose of single tasking? It will keep on doing one work forever. So while one is going to keep on doing that work forever, and the only way to turn off that work is shut down the system. Hence, we call this as a single tasking embedded system application. Single tasking embedded system application. Single tasking means only one task it will do throughout its lifetime. But is your desktop computer doing only one task? What it is doing? It is doing multitasking. It is doing multi-processing. So it is executing thousands of programs which you are not aware about. Behind the scenes, it is executing thousands of programs. In front of you also, it is executing your programs. So it is a multi-processing, multitasking architecture for a desktop computer. But for our embedded computer that we are learning about, it is not now going for multitasking. It is only going for single tasking. So you have to define, do you want this task to execute only for once, or you want this task to execute forever? If it is only for once, then this is how you define your program. This is how you define your program. So we only do this when we want to test our logic. Once our logic is tested, then we will always preferably go for this kind of architecture. And this is called as the super loop architecture. Okay. Can I go ahead if all okay? Can I go ahead? Okay. So let's take another application around embedded C. From now on, embedded C programs I'll call it as ECPs. Okay? No need to write it in the syntax. Write an ECP. Write an ECP. Write an ECP to simulate an electronic dice. Write an ECP to simulate an electronic dice. An electronic dice. Okay, to simulate an electronic dice. Taking two variables. Taking two variables, namely dice face, dice face, dice face for face value of the dice, dice face for the face value of the dice, and dice face for the face value of the dice, and roll variable for showing what we call rolling of a dice. For roll variable showing rolling of a dice. For roll variable showing the rolling of a dice. Triggering the rolling of a dice, not showing. For roll variable to trigger the rolling of a dice. Roll variable to trigger the rolling of a dice. Okay, to trigger the application should initially show a default face value. The application should initially show a default or random face value. The application should initially show a default or random face value. And should remain that and should remain that and should remain that as long as role variable and should remain that as long as role variable is 0. As long as role variable is 0. When role variable changes to non-zero, when role variable changes to non-zero, when role variable changes to non-zero, the die space should change randomly. The die space, when role variable changes to non-zero, the die space should change randomly. The die space should change randomly until role variable returns to 0. Until role variable returns to 0. Right? So this is a very simple embedded application, embedded C based application. Let's try to create it. Now in this embedded C application, there is nothing specific about a hardware here. It's only just a matter of using memory variables. No specific related hardware should be specially configured over here. It's just a logic being implemented by the use of memory variables. So let's remove this from the compilation. Let's create a new source file and let me name this source file as electronic dice. Electronic dice 1. 1 means version 1. We will be writing different versions of this as we move on from one device to another device. Okay, as we learn about devices, we will almost use the same program in those devices also, in addition with other examples. So let me add it over here. Electronic dice. So this is, so what I'll do is now I'll go for hash include. What are you expecting? What are you expecting? Hash include, what I will include? STD diode. Then make a guess at least. LPC. I told you I'm not using any specific hardware, right? I'm not going to use any particular peripheral or hardware here. So why should I include any registers related to support? So I'm going to make use of std lib. Okay, std-lib.h. Next, let's take a variable. I'll take int dice face as a variable, and then I'll take another variable. So int, okay, put it here itself. Role. Okay, so these are two variables, role and dice face. Next, main, open and close. Now, here we'll take dice face is assigned rand modulus 6. This I am assuming that you know from C language point of view. So rand of 6, it generates between 0 to 5 plus 1. So it will generate from 1 to 6 because dice are having those 6 values. Okay? And this is the value that gets shown initially. Next, let me take one more variable. Let's take seed. Okay? I'm just taking seed as a variable, and then coming over here, here is the while one loop, and after this while one loop, inside this while one loop, I'll come here, and now go for if. If roll is not equal to 0. If roll is not equal to 0, then again copy this and paste it over here. Okay, that's it. So if roll is not equal to 0, this is what is going to happen. And srand C plus plus. So I'm just putting that C plus plus there. That's it. So what srand is having, because it's a global, what C is having is a global variable, so it will be 0. And it just keeps on incrementing for every iteration 0, 1, 2, 3 up to max and value, again it will roll over. So this is an assigned integer, so its maximum value will be around 2 giga, like that, 2 giga this thing. Now, application is simply completed, save and cross compile. We have the 0 errors and a warning indicating new line, formatting, save and cross compile. Now come to debug. So in the debug, now let's come to the watch windows and give here dice face and convert that into decimal display. Give here row, convert that into decimal display. I don't need seed right now for observation. So there it is. Now I'm going to run the program. Okay. First I will debug it. So you can see this is how the program flow is happening. It is continuously there, and a random face value came up as 5. Now if I try to change the value here to a non-zero number, let us say 1. Now you can see there is a random number getting generated for the dice face value. Okay? You can observe the seed also. So that's what you can observe the seed value, and that's how the random face value is getting generated. So again, if I make this as 0, then it fixes with a number. So if I run the application now, up till now I was debugging it. I was just debugging it. Now if I run the application right now, so I'm running the application by hitting the run button. Now application is running. Now observe the change. Just executing pretty fast, the order of nanoseconds. Again I'm changing to 0. Stops. Take note.
Line up mouse terus pas ketika
the line numbers are mentioned in the sources. You have any confusions in any line number, you can just mention the line number and ask.
Gelo. Pintar dengan sekarang itu. Nah, 20 km. Wait a second, for the merge.
All noted? Okay, so far? Next. I'm removing this from the compilation. So, next example related to embedded C, which is more important in embedded C and hardly important in general C or native C. So, my intention now is to create delays. I would like to create delays. Delays can be in order of, let's say, microseconds. Delays can be in order of milliseconds. Delays can be in order of seconds. So this is my requirement. Microseconds, milliseconds, and seconds is the delays which I would like to create. Delays are a very, very crucial part in embedded programming, because when you want to do a set of operations between some operations and other operations, you will try to put in some delay so that there is a gap between this operation and this operation. It helps in synchronization purposes. It helps in seeing the output in a nice way in which you can read and understand operations that are taken. Same thing. For example, let us say you're observing a system that is booting up, or you observe your phone. When you power off your phone and you power it on, you will be observing the boot up of the phone. You will be, if you closely observe the boot of the phone, there will be time gaps between operations. Okay, there will be small time gaps between operations. First some operation will start, then after some time gap another operation will start, after some. So the whole idea about using delays is to make the output look more elegant in terms of viewing. In a similar way, delays are a very integral part of our embedded programming. If you want to make, to begin with, if you want to make a light emitting diode simply glow, then you just turn it on. But you want to make it glow at a particular rate. Okay, you want to make it on off at a particular rate. You want to create a design pattern like dancing LEDs, or you want to create a design pattern like scrolling LEDs. You maybe if you're observing when you're going on the roads, nice cars will be there, and when they hit a brake, you will see lights popping out, or when they're trying to turn left or right, you will be seeing the light design going in this direction with some lights. So you can see those lights are going with a small delays, very noticeable delays, and nicely looking delays. It just scrolls like this or scrolls like this. So why do we do all this? We want to do this to make outputs more attractive. If you go to South India shopping mall, is it Devarakonda's? Not South India shopping mall, KLM mall. Right? If you go for KLM mall, you will be seeing a lot of colorful lights. Okay, you'll be seeing a lot of colorful lights which will be attracting your view, and those colorful lights are going to change their colors, positions at certain rates. So that is all because of the delays being imposed in the application that is running that hardware. So delays are a very, very integral part of embedded programming, and delays can be produced in two ways. One is called as software delays, the other one is called as hardware delays. Software delays are generated through loops, and hardware delays are generated through timers. So to generate software delays, you need to understand the translation of how a loop happens in the compiler. This loop in this compiler is translated to generate this much delay, but the same loop in another compiler will be translated to generate a different delay. Why? Because the translators are different, have been created by different people. So how they are translating it is different. Some translations will be very optimized, some translations would be less optimized. But you have a hardware delay which you have produced for this compiler, for this hardware, and the same hardware delay for another compiler for another hardware, for the same hardware, another compiler for the same hardware will give you the same delay because that is fixed by hardware. So software delays are compiler specific. Hardware delays are compiler independent. So these are the two types of delays that you can learn about in the process of learning embedded system programming. Very, very important. You cannot be an embedded programmer without knowing about delays. So to learn about delays, did you worry about delays so far in C language? Never you worry, but it becomes very important here. So to learn about delays in embedded programming, you need to know something about frequencies of operations and delay execution time, instruction execution timings. These things you need to look at. So let us see that now. Now I will create a new source file, save this source file with the name delay test.c. Okay, delay test.c. Please do not copy anything until I tell you to copy. Just first observe. Delay test.c. So what I am doing here is I'll take main, add it into the workspace. Adding the source file into the workspace. All the other source files have been disabled, will not be part of the compilation. So I'm adding main into the workspace, into the source file, and then I'll take a variable unsigned int dly. Okay, I'm just taking a variable unsigned int dly, and after that I'll put here for, say dl1 or dly is equal to say 1000, some random number, dly greater than 0 and dly minus minus. Okay, and then I'll put the while one, which I told you that what is the purpose? We want to test this loop. Our intention is to test the loop, how much delay it is going to be produced. So I'm putting the while one over here. All following up till here? Now let's save and cross compile. So we have the 0 errors. The warning can be ignored, but I will remove the warning. Save and cross compile. So 0 errors, 0 warnings. Now, what is the frequency at which this system is operating? You need to know. So come to the debug. Come to the peripherals, come to the system control block, and then you come to what we call this block called as phase locked loop. You hit on the block on this button. When you hit on the button, here you are having a display of some information. You are having a display of some special function peripheral registers, which you don't need to worry right now. Discussion will come later. But what you need to look at is crystal oscillator and processor clock. So crystal oscillator has been given here as 12 megahertz and the processor clock is 60 megahertz. So the input frequency for the input crystal frequency is 60, but the processor is not working at 12 megahertz. It is working at, the input frequency is 12 megahertz. Processor is not working at 12 megahertz. Processor is working at 60 megahertz. That is 5 times of 12 megahertz. So this is the frequency of operation. Now for this frequency, can you calculate the time, please? 60 megahertz. Convert it into time. T is equal to 1 by f. Do it. Take your calcs. All of you have your mobile phones. Now is the time where you should use your mobile phone.
कॅल्क्युलेटर काढत नाही काय करायची
How much? 0.016 watt. What unit? Okay, give me a list of few more decimal points. 0.016 6 all 6. Okay, 7 here. That's it. Okay, so okay, whatever, all 6, all one small point, the difference it makes. So put here 1. Okay, put here 2. Put here 3. So this 0.016, now what is it? The frequency, this is in terms of seconds, right? So if I want to convert this in terms of microseconds, sorry, nanoseconds. Convert it into nanoseconds. So nanoseconds means how much will it be? This is 1, 2, 3. So this will be 16.66 into 10 power minus 3. What is minus 3? Is this seconds or nanoseconds or what it is? Minus? Nanoseconds is minus 9. What is this value? What is the unit of this value? 1 divided by 60 megahertz. Megahertz is 10 power 6. So 1 divided by 60 gave you 0.0166666, like that I'm putting there. Okay, into 10 power minus 6, right? Now 1, 2, 3. That gives us 16.66 into 10 power minus 3 into 10 power minus 6. So that means 6.66 into 10 power minus 9. That is 6.66 nanosecond. Now did you get it? So the time for one cycle is 16.66 nanoseconds. One cycle of execution. One cycle of execution is 16.66 nanoseconds. How many cycles of execution would be there probably in this for loop? Do you have an idea? Do you have an idea? Again, I am asking my question. Listen to the question carefully. One cycle of execution is taking 16.66 nanoseconds. How many cycles of execution do you think is happening behind this for loop? This is the real core embedded discussions. Do you think it is 1000 iterations? Because I have given 1000 here. Huh? Do you think it is 1000 iterations? 1000 cycles? Or less than 1000 cycles? Or more than 1000 cycles? It will be more than 1000 cycles. So the answer to this question is you need to know what is the translation for this for loop. When this for loop is translated, what is the code it will generate? Translator does what? Translator's job is to convert source code written in C into source code of assembly. So you need to know what is the assembly code generated equivalent for this C source code. Assembly code may be one I'm just saying so. Maybe one instruction, maybe 2 instructions, maybe 3 instructions, maybe 4 instructions, maybe 5 or 6. I am not the translator, right? I am not the translator. So when translator translates this C source code, it is translating it into how many assembly instructions that you have to look. In that, how many assembly instructions few assembly instructions will deal with initialization of the delay 2000, and this assembly statements will deal with testing if delay is greater than 1000. Then next assembly instruction will decrement. If this condition is true, then it will decrement and then iterate. So there will be decrement, iteration, decrement, iteration, decrement, iteration. That will happen many times. This will happen once. This will happen once. But this one and this one will happen many times until this condition fails. So for this entire for loop, what is the translated code in terms of assembly? And every instruction, if it is going to take one clock cycle, and there are 5 instructions, assuming, I'm just saying assuming, okay, because I have not translated it. So if one instruction is taking 1 clock cycle and there are 5 instructions, so 5 into 16.66. So take it approximately 90 nanoseconds. So 90 nanoseconds it is taking for one iteration. 5 instructions are there approximately. One instruction, if 1 clock cycle is taking 16.66 nanoseconds, 5 instructions is taking 5 into 16, 90 nanoseconds. 90 nanoseconds is repeated around 1000 times. That is the time that will be produced by this loop speaking. Clear with that? So whatever I have spoken is without knowing the details of what is the translation. We can know what is the translation by simply looking into the object code, but that is not what we need to do now. We are trying to focus on embedded C, not on assembly. So how to deal with this is we use the tools that are available. So now look at here, this is the for loop with the value of 1000. You can see here a timer. For the back people, I'll make it slightly visible. So you can see here a timer shown here, which tells us the time of operations taken place so far, including the startup code, everything till this point it has come. Okay, startup code till this point it has taken this much. Now what I'm doing is I'm right clicking here. I'm right clicking and coming here and say reset stopwatch. This is a very nice handy debugging environment which helps you to write good programs. So if I reset it, now it has been reset. Now with this reset state, I am now going to execute the for loop, and we will come to know what is the time it is taking at operating frequency of 60 megahertz. So when I execute this for loop by hitting F10 on the keyboard or else by hitting this button, okay? If I hit this button called as step over, or on the keyboard I hit F10, it will execute this statement. Now observe here. So I'm executing, statement is executed. Now you can observe here what is the time taken. Check it out. What is the time taken? Can you see that? 0.0008343. 0.0008343. This is the time in terms of seconds. It is showing you in terms of seconds. So 1, 2, 3, 4, 5, 6. 83.4 into 10 power minus 6. So that is 83.4 microseconds. So this for loop has taken approximately 83.4 microseconds at an operating frequency of 60 megahertz. If the operating frequency changes, the timing also changes. Clear with this? Okay with this? Yes? Okay. So it is generating 83.4 microseconds for this loop of for loop. Now what I'll do is let us come back. Are you finding intensity here in the programming? Are you finding this programming intensity? Intense. See, I'm dealing with hardware. With respect to hardware, I'm talking frequency of operations, what is the time produced, all these things. You never talked about this in C. But here in embedded C, everything we talk about, every statement that we want to write in embedded C will be related to hardware. That is what I'm trying to stress on. The way you treat embedded C, the way you try to learn embedded C is an entirely different process and what we call commitment compared to C language. In C, you assume keyboard is working. You know monitor is working because you are seeing something. But in embedded C, we don't assume our device is working. Input device and output device. It is our duty to know whether it is working or not and then make it work, if we can make it work, or replace it with another device. So, now what we do is, I will come here, create a function, void delay microsecond, okay, void delay microsecond, and put here DLY, you assign int DLY, microsecond I'm putting, and then coming over here, I will remove this from here and cut this and paste it here. Okay? Now, so this was generating approximately 83.4 microseconds, right? This for loop was generating approximately 83.4. Now, for a iteration value, this is mathematics of school language. This is called as unitary method. Unitary method. If a value of 1000 gives me 83.4 microseconds, I want 1 microsecond. How much? So 1000 divided by 83.4. What do we get now? Take the calcium. So 1000. Okay, here we have to take normal calculator. So 1000 divided by 83.4. So that is giving us 11.99. Let me round it up to 12. Okay, I'll round it up to 12. So here I'll put 12. So for an iteration value of 12, it will be giving me approximately 1 microsecond. Right? Now look up here. I'll put here delay. I'll put here delay microsecond, let us say 1, delay microsecond, say 100, delay microsecond, say 1000, delay microsecond, say 100,000, and delay microsecond, say 1,000 or 1 million. So what can you understand from this use of the function? This will approximately produce 1 microsecond. This will produce 100 microseconds. This will produce 1000 microseconds, which is 1 millisecond. This will produce 100 milliseconds. This will produce 1 second. 1000 microseconds is 10 power 6 microsecond. So 10 power 6 microseconds is 1 second. Now let us observe. Save and compile. Okay, we have a microsecond change here. Right? Save and compile. Now come to debug. Now please once again observe, I am resetting this. Let's slightly increase the font for visibility. Okay. Now I am executing the first function by debugging by pressing F10. Okay, first function is executed. You can see what is the time I got. How much did I get? 1.0000122. So if you take till 6, it will give you 1 microsecond approximately. Next, let's reset this. 1 microseconds, 220 nanoseconds approximately it is there. So I'm taking the microseconds only now. Now I go for this. Something went wrong here. Okay, yes. Mistake. It's a coding mistake that happens. So what I do is I go for multiplication. It was a logical mistake. So whatever number I pass here, that will be multiplied by 12. 1 into 12 is 12. 100 into 12 is 1200. So if 12 gives us 1 microsecond, then 100 into 12 gives us 100 microseconds like that. So that was a logical mistake which they made. So let's go back again. Now save and cross compile. Come to debug. Okay, again observe here, reset. Now, first one gave me 1 microseconds, reset. You see, 100 microseconds, reset. 1000 microseconds, which is 1 millisecond, reset. 100 milliseconds, reset. And last one. 1 second. Take that. Stop here for today.
Yes.
Participate in the lab, participate in the class, you will learn the subject happily. You fail to participate in the lab, participate in the class, subject will always be tough.
गुरु आमचं झोपायला लागलं खरे का नाही 8:30ला बेल असतो का त्याच्यामध्ये साडे 1 तास 5 झाला मोठी माणसं जगन्नाथ मोठ्या मित्रांमध्ये वाणीचं
Huh?
वगैरे माहीत नाही पण
It is capital U, capital S, symbolizing microseconds
हाँ.
abbreviation.
हां
It's a variable name.
बुंग झालं का झोपलं का
All done? So how many programs we did today? Copy ROM to RAM, version 2. Next, electronic dice and delay test. Try to practice these 3 programs and understand before tomorrow's class.
गेलं ना बरं आता 11-12
बाड़ी